Hi folks, this is the unit on machine learning and cloud services. It was offered as part of a course at Indiana University, but as part of our overall online resource for big data and cloud computing. I'm Jeffrey Fox, the instructor, and it's actually now April 2019. Thank you. So this unit is to cover parts of machine learning. And the students in this course, among other things, build projects which deliver cloud-based machine learning services. So we try to help them in this unit by reviewing machine learning. Of course, other units have gone through details of cloud computing and Docker and Kubernetes and things like that. We cover aspects of linear logistic regression, but only a very formal discussion. The practical part is in a different set of lectures. We also have significant discussion of support vector machine and clustering, and a review on Kate nearest neighbor, also discussed in another lecture, principal component analysis, PCA, hidden Markov models, and latent Dirichlet allocation. Okay, let's look at regression, where we have both logistic regression, where we're doing classification. The observable is effectively 0 or 1, or linear regression, where the result is going to be a number, and the data is labeled by numbers, such as the year or the model of the car or what have you. And the basic idea is the same for both logistic and linear regression. You have a set of training data, which in the old days used to be all the data, but nowadays maybe you put some aside as testing data. The training data is labeled by the independent variables, called X later on. The data itself is called Y. Then we have the model parameters, which will end up being called alpha and beta, which are the dependent variables determined from the data. Then to determine the model parameters, we write down the likelihood, which is the same, effectively the probability, in that this ends up being the product of the probability of observing each of the training data values, and then you have that total likelihood, and you need to maximize it. This is the famous maximum likelihood principle, and you find the model parameters that maximize this likelihood, and that is just an optimization problem. We have later on a few remarks on optimization. Underlying machine learning is optimization. Optimization is not always machine learning, because optimization is just trying to find typically the maximum or minimum of a function, and that may or may not have much to do with data. When I did optimization throughout my life, and initially it was called data analysis, and it was physics data, and we didn't call anything machine learning. Anyway, but now a lot of machine learning is optimization, and solving this optimization problem for linear regression is very simple. It's just algebra. We'll sketch that. Logistic regression is actually, even in some sense, a simpler formula, but it's not got a sort of cosmic solution, which is you can write down. You have to just do simple iteration. Notice all these functions are nice. They end up being obviously positive sums of squares, and when things are obviously positive, then you'll find your iterative optimization will always converge. The only issue is that sometimes it converges to local minima rather than global minima. In logistic regression, it will converge to global minima. Okay, thank you very much let's move on to discuss logistic regression. Or yourself. In logistic regression, we have an exponential probability, 1 over 1 plus exponential of minus t of x, where t of x is just a linear function of the parameter x, which labels the observations and the alpha and the beta of the model. And that's what we're trying to find. And we have the probability that y equals 1. I mean, the observations are y, they're labeled by x, and we have probability y equals 1 is 1 over 1 plus e to the minus t of x, and the probability y of 0 is e to the is just 1 minus this, and you have a nice plot of probability which looks like this. Well, this is infinity, x equals infinity, and here's x equals minus infinity. It goes from 0 to 1, and it has a nice, smooth transition at this point here, and the alpha and beta determine the value of that point. And so if you have a whole bunch of measurements, x1, y1, x2, y2, xn, yn, then we think of it here, we have a probability p, and we just write down the observations because we know for each of the x's what the y is. The y's will either be 0 or 1, and then we end up minimizing this quantity here. We maximize the product of the probabilities, or we minimize the negative of the log of the total probability. And that's the log of a product is the sum of the logs. We just get the simple linear function which adds the log probs. That's very, very universal term function form. Now we come to linear regression and its structure, and now the probability is different, although actually y of x, the model, is actually alpha plus beta times x, where x is the observed value and alpha and beta the model values. If you want to generalize this to lots of x's, where your observations depend on many variables, then we have alpha plus a whole bunch of betas. Alpha is just put in there to get a normalization because probabilities have to be between 0 and 1 and things like that. Now, we have a very different probability because it's just Gaussian, because we're assuming that this is this type of observation where the deviation of the measurement from the theoretical value is due to some errors. Typically, those errors are distributed Gaussianly, and so you end up with something like this: alpha plus beta x minus y all squared over twice the standard deviation squared. And here you see that, so then if you take these exponentials, you multiply them together, then you get a sum inside the exponential. Then when you take the negative of the log, you just get this very simple form, which is always called chi-squared. Well, actually, this one is chi-squared, and that is another more popular term is least squares, and there's endless discussions of this, and it is really straightforward to minimize this function to find alpha and beta, and we just sketch that in the next slide. So if we minimize this quantity here, we get this. We just look at this, it actually ends up as a quadratic in alpha and beta, and we can then complete the square, and then just use traditional manipulations to make us squares have an obvious minimum. But a simpler way is just take that the function we now have up here without even completing the square, and set the derivatives of alpha and beta to 0. That gives you the derivatives are going to be 0 at a minimum, and you can always see there is a minimum because it's a sum of squares. Sum of squares has to be bounded below by 0. That's why these optimization formulae are nice, because when you have sums of squares or something which is guaranteed to be positive, whatever you do, then your whole approach to minimization is much more straightforward because you're almost guaranteed to get the right answer. Well, not guaranteed, you're guaranteed to get a stable answer. Whereas if you take messier functions, then the thing diverges and roars off to negative infinity, and it's all a disaster. Much harder. And I spent a lot of my life solving those hard problems. Then if you just set the derivatives to 0 and solve then you get two equations for two unknowns. These are linear equations in alpha and beta, and you can solve them straightforwardly, and you get formulae like this for beta and formula like this for alpha. And given you have alpha and beta in terms of the observations, y sub I, and that labeling parameters x sub I, then you can actually do an estimate or an inference of the value of y for any given x that comes along later. Even when you have lots of independent variables, then x, then you can still solve for alpha and beta using matrix arithmetic. Okay, thank you very much. That's the end of our very brief discussion of logistic and linear regression. Thank you.